Okay, so let's start. Thanks for coming. So I want to first finish off where we left off last time, which is finalizing multiclass. So we talked about multiclass, and I want just to explain this in the context of SVM. I think this is a more general and interesting context. So you all know SVM. We talked about the binary case, where the goal is to maximize the margin, or equivalently, you should make sure that you agree that it's equivalently, minimize the norm of the weight vector while making sure that all the other points satisfy the constraints, and the closest point to the hyperplane have score plus or minus 1. So these are the support vectors. So that's the binary SVM. When we move to multiclass, now, just like we discussed last time in the one versus all context, we're going to have a lot more weight vectors. We're going to have one weight vector per class label. But as opposed to one versus all, where we learned each one of the weight vectors independently of the others, how did we do it? We told each weight vector, label number 1 is your positive, all the rest are your negative. And then second weight vector, label number 2 are your positives, all the rest are your negatives. So we really learned k weight vectors independently. In the context of multiclass SVM, we do learn k weight vectors, but they are not independent. And they are not learned independently. I'm going to show this in a second. And just like in SVM, we're going to maximize a margin, but it's going to be a slightly different margin. It's the multiclass margin. Equivalently, completely analogous to what I said above about the SVM, we're going to minimize the total norm of the weight vectors while making sure that the true label scores at least one more than the second best one. All right? So before, we made sure that they score 1, at least 1. Now, it's at least 1 more than the best, than the second best.
By 1, you mean 1 more correct classification, or 1?
So in the hard SVM, we basically want the WXT to be greater or equal than 1 in absolute value. Now it's going to be greater or equal. The difference between the top one and the second best is going to be greater or equal than 1. So it's written here. So we are maximizing this. We are optimizing this. The L2 norm of the weight vector, but this time it's not a single weight vector, it's the sum over all the k weight vectors, such that yi is our true label, right? The example is xy, yi. So the dot product wyi with x minus the dot product of the wk with x has to be greater than 1, and we want this to be for all k's. Okay, so it's separable. It's not greater than 1, but rather it's greater by at least 1 from the other dot products. So the score for the true label is higher than the score for any other label. That's what we are. That's what we want, and this is where the dependency comes in, right? So it's not just greater than a fixed number, but rather it's relative to the other weight vectors. Yeah.
I'm not sure I understand, like, the true label minus the best classifier minus the best weight vector.
So what would I write here if it was just binary? You will not have sum here, right?
Yeah, and below it.
And here, you will not have this. You'll just have wyi, sub yi, x greater or equal than 1. Right? No,
W sub k, that is the best.
no, not the best. I'm doing it for all of k, so I'm not saying best. It's actually going to be the best, but the way I'm saying it for all k's, right? So it's going to be at least gap of 1 from the best.
And will all data sets always allow for this condition?
I don't know. So that's a completely different thing. So this is the hard SVM formulation. Whether it's being satisfied, whether there is a W like this, who knows, right? But it's the same question you would ask for the binary, right? So if it's linearly separable, there is a W like this. If it's not linearly separable, I will not be able to do this. We will have a soft version, right? But that's the requirement, that you separate it from the others. Okay, so in the general case, I'm going to take this and I'm going to add, as before, the slack variable. So I'm going to add here a slack variable, so it's not greater than equal to 1, but rather 1 minus this psi I. And the condition, or what I want to minimize, also is going to take the psi into account. So instead of just minimizing the norm of W, I'm going to minimize the norm of W plus the sum of all the slack variables, and I'm still going to have this C constant that we're going to tune, just like before. So psi is also minimized here. Okay, so basically, it's really the same kind of idea that we had before. I have a set of positive psi's that allow me to make mistakes, basically. So it allows some of the points to not be classified correctly during training, but I want to minimize how much this happens. Okay, so the reason I'm mentioning it is because it's interesting to realize that it's different than 1 versus all. It's similar to 1 versus all in the sense that you're going to have k labels and therefore k weight vectors. But it's different in the sense that I'm optimizing really all the W's together. So that's the important thing. It comes with generalization guarantees that are similar to the binary SVM. You can train it using, as before, using different optimization methods. We don't really care about this because you're going to use a package, but essentially it's going to be a gradient descent algorithm. So just to summarize, so in training, we optimize a global objective that takes all the W's into account. In predictions, you have all the W's, the KW's, and you do winner take all. Argmax over WI dot product with X. And again, it's important to realize that you are working here in a much, much higher dimensional space because the number of weights that you have is K, the number of labels times N, which is your dimensionality. Okay, so there are reasons, theoretical reasons for why we want to do it this way. Why do we optimize this global SVM rather than the 1 versus all? And really, everything boils down to this picture, which I showed last time, that if you just do 1 versus all, sometimes it's not expressive enough. Right? You cannot separate each color from the union of all the others. This global optimization allows you to do it, and there's some theoretical explanation of why this happens. I'm not going to explain it. Yes?
You talked about like generalization guarantees. Like I think I read somewhere something about like generalization or something like number of support vectors over number of examples or something like that.
Yeah, you can quantify the generalization ability in terms of number of support vectors. We gave a very weak argument of generalization in terms of just number of examples that you see. This can be improved. Yeah, I mean the bounds, even the bounds with support vector, are relatively loose bounds. Okay, so there's more information on this in the slides. I'm not going to go over it, so I'm skipping the rest of this. If people are interested, you can go and try to understand why does it make sense to learn all the weight vectors together in some sense rather than independently, but I'm not going to discuss it. So I want to move to a new topic, which I promised to do last time. Before that, let me remind you of a couple of things. First of all, projects. People that are doing projects, you have to come to talk to me about it at least once, more if you need. Surveys. So about a third of you or so did the surveys. Please do it. As I said last time, if 80% of you do it, we're going to give extra credit. So please do it, convince your friends. It's important for us to see what you think. Okay, so a few other things that I have to start talking about. There's going to be an exam. The exam, as it says on the website, the standard day, the assigned day to us, which is December 17. It's going to be in Chem 102, so there's going to be a lot more space, not going to be as crammed as in the midterm. Similar to the previous midterm. In fact, even though I've written here 75 minutes, it's going to be longer because they give us the room for 2 hours, so there's going to be a little bit more room. It's cumulative, so basically it's a final. You have to know everything. The focus is going to be a little bit more on what happened since the exam, even though all the material here is cumulative. I mean, you cannot understand what we are doing in the later part of the class without understanding what we've done earlier. And the material is everything we covered in class. So if something is on the slides but I haven't talked about it, it's not in the material for the exam. I'm giving some examples here. So we talked about boosting, but we didn't talk about boosting the confidence, not in the exam. We talked about multi-class classification, one versus all, we did talk about. All versus all, we did talk about. We didn't talk about error correcting codes. We didn't talk about constraint classification, even though it's in the slides, so it's not in the exam. So basically, what we talked about is covered. There's one other comment that I want to make, given your question. You don't want it to be just like the midterm. It's not going to be just like the midterm. But this is already in response to some of the comments that we did get. So the class is on applied machine learning. Now, which means that you have to be able to understand machine learning and you have to be able to apply machine learning. I cannot test you in the exam on applying things. I cannot ask you to write programs. And therefore, we kind of split it and we focus in the exams mostly on the understanding and in the homework mostly on the applying. Altogether, hopefully, you get a complete pictures. You cannot expect that what you see in the homework is what you're going to see in the exam, and vice versa. So each one of them is worth about half the grade. So that's how we're doing it. So, so the exam is going to be more about understanding, and as I said, you're going to have a lot more time. Questions? Yeah. I don't think so. They will be. They are okay. 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 So I want to move on and talk about a different paradigm in machine learning. So what we've done so far, we can call error-driven learning. So everything we've done was driven by running the learning algorithm, getting errors, and see what happens. So really, we can think about the data generation process as governed by some probability distribution, d of x, and then we have a labeling process that is governed by d of y given x, and together we have a joint probability distribution over examples, comma, labels. So it's important to realize that we don't know d. If d is known, there's no problem. There's no learning. You just predict y as the argmax of the distribution of y given x. But what we are, the area we are at is that we don't know d, but we know that there exists a d that governs the generation of the process, both in training and in test, and we are trying to find the best hypothesis. Here is one option. Find the argmin relative to minimize the number of mislabeling, the case where h of x is different than y. Now, in general, we did more things than just that. We did it in what is called the discriminative or direct learning paradigms. What we're going to move to do today is what is called Bayesian learning or generative type of learning. So just to make a distinction, a very sort of rough distinction, I'm going to go again to the problem of text correction. We've seen this before. I saw a girl at the park. I want to be able to write a program that corrects it to I saw a girl in the park. So identifies that it is a mistake and corrects it to in. So in the direct learning paradigm, what are we doing? We're basically looking at the problem as a problem of learning from examples. Look at a lot of examples, positive and negative, discover some regularities in the data, and use this to have some prediction policy. So specifically, I'll come up with a function. The function could be very simple as if you see the word D occurs after the target, change the target to in. It could be a more complex function, linear function, decision trees, random forest, whatever you want, but basically the idea is that you have some function that looks at the input and does something. And all the assumptions that allow us to learn these functions are factored into the assumption of hypothesis class. We are learning this class of functions. We're feeding all the examples into a learning algorithm that chooses a member in this hypothesis class. So the bottom line is that we are trying to learn a function or approximate a function h that map x to y, x instances, y labels, by estimating the probability of y given x. And we've done it in many, many different ways. All of them fall under this paradigm. Maybe the most general scheme that we've written is here, right? So we want to minimize the sum over all examples, 1 to m, the probability of xi comma yi, loss function of h of xi, the function that we are after, comma yi, plus regularization. And we plugged in for L different loss functions, right? So 0, 1 loss functions, L2 loss function, each loss function, exponential, you know. And in the homework you've done a couple others. So that was the general paradigm. And we also have some guarantees, right? So we spent some time figuring out that the reason this is going to work is because we have some theorems that say if you find an algorithm that minimizes this thing, the loss on the observed data, then learning theory is going to guarantee that you're going to do okay in the future. What are we going to do starting today? We're going to move to a generative model where we are really going to model the problem of text correction or any other problem as that of generating correct sentences. So there's going to be some probability distribution that governs what's happening. It's going to generate correct sentences. And our goal is to learn this model. Once we have this model, this generative model, we're going to use it to predict. So really, in principle, we're going to learn a probability distribution over all sentences in the case of this text correction. In practice, we're also going to make some assumptions. We're not going to learn in the most general way. But once we have this probability distribution, we're going to use it to estimate which sentence is more likely. So we compute the probability on the left, probability of the sentence, I saw the girl eat the park. We compute the probability of I saw the girl in the park, and we compare. Now, in practice, again, as I said, we're going to make assumptions, and the prediction policy or the decision policy is going to depend on these assumptions. And it's going to take us a week, but we're going to see that in practice, sometimes these two conceptually different paradigms boil down to doing the same thing. But they are very different conceptually. In particular, the guarantees are that we are assuming the right probability distribution, or saying it better, the right family of probability distributions. So we're going to assume a family of probability distribution and then look at data and choose a specific member that we say, this is the one that generates our data, and now we can use it to make predictions. So the bottom line is that we are approximating the joint probability P of xy, which is P of x given y times P of y. And the reason we call it generative is because we actually care about how the data x is generated. And we'll see examples today that will clarify. So we really care more about x than we cared about x, the data itself, in the direct paradigm. Yes?
So if you have like a model, even what the model is, at the beginning of the process, should we ask ourselves, like, basically, can you approach the same problems with both types?
Yeah, definitely. It's just different approaches, same problems exactly, and we're going to get there. So we'll see examples. So before I start, really, I want to give one clarification that is sometimes confusing in the literature. So there are really two different notions. One notion is learning probabilistic concepts. What is a probabilistic concept? It's something that takes an x and maps it to 0 to 1. Now, you can learn probabilistic concepts with direct learning. Everything that we've done before, if you think about it, really produces a classifier that really returns a number between 0 and 1. And there's Bayesian learning, which uses probabilistic criteria to select a hypothesis or to make predictions. The hypothesis could be deterministic, could be a Boolean function. You still use the Bayesian theory in order to do it. So really the difference is not in the hypothesis that we learn, but rather in the process that we use in order to learn. And we'll see examples of that. Okay, so now in the next 20, 30 slides, there is a survey of basic probability. I mentioned it last time. Hopefully you went over it, or you went to some of the pointers that we put on the website, or you went to your favorite basic probability book. I'm going to assume that you know something about basic probability, and I'm going to go to Bayesian learning. Okay, so what is Bayesian learning? So our goal is to find the best hypothesis from some space, capital H of hypothesis, given observed data, which we think about as evidence. Best, what is best? Best for us is going to be the most probable hypothesis. In order to even talk about most probable, we have to assume some probability distribution. We're going to assume some probability distribution over the class H of all hypotheses. And in addition, we need to know something about the relation between the data and the hypothesis. Think about a coin problem, which we're going to get into in some details in a second. So you have some hypotheses for, I have a coin here, which is nice, of what is the bias of this coin. Some of you might think it's fair coin, some of them might think it's a biased coin, and it's 90% probability it's going to be head, but you have some relation between the data that you see and the hypothesis. If I'm going to toss it 100 times and you'll see only heads, you will see, okay, it's probably the hypothesis that head is a lot more likely. If you'll see it's about even, you'll say, oh, it's the other hypothesis. So you have a notion of relation between the data that you see and which hypothesis drove this data. So now, in the next week or so, we're going to be Bayesian, and you can be Bayesian about many things, and I'm going to give examples. You can be Bayesian about which hypothesis you choose, or you can be Bayesian about which decision you're making. And these may not be exactly the same. I'm going to give examples. So what is the game? Everything that we need to know about Bayes learning is in this slide and the next slide. So there are really a few components, these 4 components. P of H, the probability of, the prior probability of the hypothesis. This is something that we knew before we started learning. We have some background knowledge that gives us a prior probability distribution over all the hypotheses. P of D is the probability of the data. I look at a sample of the data. What is the probability of this, of observing this data? It has nothing to do with the hypothesis. P of D given H is the probability of observing this specific sample given that H is my current hypothesis. Right? So different H's for the same data, P of D given H is going to be different. And P of H given D is what we care about. What is the probability of H, the hypothesis, given the data that we've seen? This is called the posterior probability, and this is the stuff we really want to compute. How are we going to compute it? We're going to compute it as a function of the top 3 things there, and the only tool we have is this Bayes theorem. Bayes theorem says that P of H given D, which is what we care about, the posterior, is P of D given H times P of H divided by P of D. Now, you actually knew that because if you take P of D and move it to the left side, all there is here is just product rule of distributions. P of D times P of H given D is the same as P of D given H times P of H. One of the first things you see. But now we're going to write it this way because we want to make prediction. We want to be able to compute the posterior P of H given D. Just as intuition, it should make sense to you that P of H given D goes up when P of H goes up. If you have a more likely hypothesis, it's more likely also in the posterior once you've seen some data. It also goes up with P of D given H, right? Because if the data is more likely given this hypothesis, when you see the data, this hypothesis is more likely. And it should go down with P of D, because if this data, irrespective of any hypothesis, is very likely, then it does not explain the hypothesis. So P of H given D is less likely. So this, hopefully, intuition is something that you can convince yourself. Okay, so what is the game we're going to play here? The learning scenario is we have a bunch of hypotheses H, capital H, models, you can think about them. We want to find the most likely one, the most probable one. And we're going to call this most probable hypothesis the maximum a posteriori hypothesis, or the map hypothesis. And we're going to use Bayes theory to compute it. So basically what I'm doing here is I'm rewriting what I did before. So the maximum posteriori hypothesis, H map, is the argmax over all possible hypotheses of P of H given D. I'm writing here Bayes' rule. So it's the argmax over all H's of this product. Now think about it. This does not matter, P of D. So I can just write argmax of P of D given H, P of H.
Does it not matter because it's the same number for all of them?
For all the argmaxes, argmax is over H, and P of D is a constant there, so I can take it out. So the value is going to change, but the max, the argmax is not going to change. Okay? Okay, so there's another notion here. The general notion is this H map, the maximum posteriori hypothesis. Now you could say, you know what? I don't have any a priori preference for H1 over H2 over H3. I don't care. So I have a uniform probability distribution over the HIs, which is written here. P of HI is equal to P of HJ for all I and j. And in this case, I'm going to eliminate also this P of H thing because it will not matter. So now, instead of H map, I'm going to call this HML for maximum likelihood, the most likely hypothesis, and all I care about is argmax over all the H's of P of D given H. Because, again, P of lowercase h also disappeared. So look at the top here, right? So here it says argmax over H, P of D given H, P of H. Now, if all the H's in capital H have the same number here,
because you're making them equal.
I'm making them equally likely, then it disappears from the argmax decision.
You choose not to make them equally likely?
Yeah. So there are two options. I have two options. One option is I'm computing H map. Another option is the special case where all the H's are equally likely a priori, and there this H map becomes HML. All I care about, really, I'm choosing the hypothesis. This is how you can read this rectangle here. I'm choosing the hypothesis that explains the data best, right? The hypothesis for which P of D given H is the highest, because I don't have any a priori assumptions on the hypothesis. Okay, but let's start with an example, and we'll see. So my first example is going to be this coin, and let's assume that I have two options. I show you the coin, and we don't know whether it's fair or it has a bias 60% in favor of head. That's the learning problem we have. Why is it a learning problem? I'm learning one parameter, which is the bias of the coin. Is it 50% or is it 60% head? Okay? How do I learn? Bayes' rule says, or Bayesian theory says, do experiments, right? Look at the data. So H1 has P of H 0.5. H2 is the hypothesis that H1 is the hypothesis that the probability of head is 0.5. H2 is the hypothesis that the probability of head is 0.6. And now I'm going to use Bayes' theory, Bayesian learning, in order to decide which is true. I'm going to start with priors. My prior for the H1 is 0.75%. My prior for H2 is 0.25%. So I believe that it's a fair coin. Okay, so now, how do we decide? We need data. I'm gonna run experiments. My first experiments, I'm gonna toss a coin, I got head. Now that I have data, I can figure out what my prediction is gonna be. What is my chosen maximum or posteriori H? Let's compute it. So first of all, so I have to touch all these components of Bayes' theory that I showed on the previous slide. What is P of D given H? That's something that we know from home. We know that we made this assumption. The probability of the data given H1 is 0.5. The probability of the observed data given H2 is 0.6. Everyone agrees? what is the probability of the data? Again, this is something we can compute given what we already know. So the probability of observing this data is the probability of observing the data given H1 times P of H1, plus the probability of observing it given that it's H2 times P of H2. This is called total probability formula. You've seen it. If you're not fluent, go and convince yourself, okay? And now I can plug in numbers, so it's 0.5 times 0.75 plus 0.6 times 0.25, that's what I get. So the probability of observing head is 0.525. Why is it 0.525? You have to convince yourself that you get it. The reason is really my previous assumptions, right? The way I set up the model, right? Okay, and now I can compute the posterior. That's what I care about. P of H given D. Bayes' rule says that P of H1 given D, P of D given H1 times P of H1 divided by P of D, I get this. P of H2, I have to do it for all the H's, right? And then I'm going to do argmax. P of H2 given D, again, I'm using Bayes' rule here, and I'm plugging in the number, I got this. So what is my prediction now? My prediction is that H1 is the chosen hypothesis. This is the winner of the argmax. Yes?
Where did the 0.75 and 0.65?
My assumptions, prior, here. I started with this belief. That's a belief. And if you had other beliefs, all the numbers are going to be different.
What do you base your beliefs off of?
No answer for this, really. This is an exercise that we're playing. In life, how do you get priors is really one of the most important questions in practical machine learning. But now we are just being technicians. So we plug in some priors and we see what the theory says. I'm not addressing how I got the priors. Yes?
Like the effect of the data was the use of one observation. Is that the 0.5 and 0.6? Is that the...
Yeah, so I had some assumptions. These are the priors. Yeah. And I made one observation. And you know, my prior was 0.75, 0.25. Now, after I observed one data item, my belief has changed. Now I think that the probability of H1 is 0.714, and the probability of H2, the second hypothesis, is 0.286. This makes sense, right?
But the 0.5 and the 0.6, those are also, that's a combination of the data and your belief? Or is that
No. 0.5, these are facts. So I have two options. This coin, this is physics. Someone told me this coin has only two options. It's either a fair coin or it's a 0.6 head coin. That's fact. Now, do some experiments and decide which is which. Before doing experiments, I have my prior. Where do I get the prior? I don't know. But I believe that it's more likely to be a fair coin, 0.75. And then I start to collect data. I collected only one data item, and now my belief in the fact that this is a fair coin decreased, which hopefully makes sense to you, right? Because I got ahead. So I should believe more in head, or in a head bias than in a fair coin. Now, two comments here. So first of all, head, I used a different prior. It would be different, right? So For example, if I would have prior 0.5 for H1 and H2, now I would actually think, so this would be the maximum likelihood approach, what I call the ML approach, because my prior is the same for all hypotheses. I would actually believe now that it's a biased coin, because I got ahead in my first experiment, and before I was uniformly believing in H1 and H2. Right? So really the priors play a lot of role here. That's one comment. Second comment, try to do it with 100 coin tosses. So let's assume you try 100 coin tosses and you got 70 heads. Do the math. It appears in the next slide. I'm not going to go over it, but simple combinatorics, you can do it. Even before you do it, you should convince yourself that you will believe that the coin is biased. Why would you believe that the coin is biased? Because I told you I did this experiment, 100 coin tosses, and I got 70 heads. You should believe, if the math works out, that it's biased, right? Okay, so that's our first example. We're going to see a couple more examples today. This is the 100 example case. You can do the numbers and you'll get it. Okay, so this is our first learning problem. What was the learning problem? I want to make sure that we get it. So we had one parameter that we had to learn. The parameter was the bias of the coin. We had a finite hypothesis space. What was the hypothesis space we had? Yeah? Two hypotheses, 0.5 bias, 0.6 bias. Oh, fair and 0.6 bias. And what we did is a simple learning algorithm, look at some data, run Bayes rule, and see which hypothesis is more probable. Okay, everyone agrees? Now, what is the real problem when we have a coin? I simplified it a bit, right? So I gave you just two options, finite hypothesis space. In real life, we're going to have infinite hypothesis space, right? Every p between 0 and 1 could be the bias of the coin. So now I want to do this same problem, argmax over all possible hypotheses for the bias of the coin. Okay, so again, I want you to think about, we went through the same kind of ideas earlier in the class. We played a little bit with finite hypothesis space where everything is tractable and we can feel it in our hands. And then we moved to infinite hypothesis spaces where things could be a little bit more abstract conceptually. We're going to do the same thing here. Now, hopefully you'll see that it's actually quite simple. So what is the problem now? Assume that you toss a coin, p, 1 minus p. So it's p for head, 1 minus p for tail. I'm going to toss it n times. Let's assume I got k heads. What is p? That's a learning problem, right? We have a model. We've seen data. I told you what the data is. And the question is, what's the value of p? What do you think is going to be the value of p? Yeah?
It would make sense for
K over M. One suggestion for K over M. Any disagreements? I think it's going to be a quarter. So who's right? I have two guesses now. One guess goes for K over M, one guess goes for a quarter. What do you think is right? What would be your way to the side. So what is the game that we're playing now? We're playing the Bayesian game, right? So Daniel will have to prove to us that m over k is more likely than a quarter, right? He has a hypothesis, I have a hypothesis. The Bayesian game is choose the one that is more likely given the data. So we have to be able to compute the likelihood, right? So it's not just choose a random number between 0 and 1, but rather choose the most likely one. So let's do this. So I'm going to compute the maximum likelihood estimate of P. So again, we're playing the same game that we played before. If P is the probability of head, then what is the probability of the data we observe? Notice that we observed k heads and m minus k tail. So I'm claiming that the probability of the data given the hypothesis P is P to the k, 1 minus P to the m minus k. Now I'm going to move to the log space. Why do I move to a log space? It's easier to do computation in the log space. This is an important comment for your next homework that will be released tomorrow, I think. Whenever you do these kind of things, dealing with probabilities, you want to work in the log space. Take log of everything and then work. Because, first of all, computations are much easier. Instead of products, you have sums. Everything is nicer. Two, there are numerical issues. If you multiply probabilities, very quickly you're going to get to 0. If you work in the log space, you avoid that. So that's something to remember if you have never played with probabilities. Remember that all your problem homework 4, the numerical part of it, you have to do in the log space. I'm pretty sure we've written it there, but I'm just reminding you. So now I move to the log space here. So instead of computing the likelihood, I'm computing the log likelihood. L of P, the likelihood of P now is the log of P, the log of the probability of D given P, log of this. It's K log P plus M minus K log 1 minus P. And now I want to maximize it. So I want to find, okay, so before I did it for H1, I did it for H2, and I looked at which value was higher. Now I have infinitely many options, so I cannot check for all of them. What I'm going to do is I'm going to use calculus. I'm computing the derivative and setting the derivative with respect to P to be equal to 0. So the derivative of this relative to P is the derivative of this expression. So it's K over P minus, because of this guy, M minus K over 1 minus P. Set this to 0 and solve this equation, you will get K over M. So Daniel was right, and this is the right intuition here, right? So hopefully all of you knew that this is the right answer. When you toss a coin M times and you get K heads, the probability of head is K over M. Now, why is this true? This is true because we had an assumption of a hypothesis space in mind. The hypothesis space that we had, or the set of models that we assumed, is the binomial. Now, I could have assumed a different model. I could have chosen a different probabilistic model that governs the generation of the coins, and I would get different numbers. And we're going to give you an exercise that will exhibit this. So everything depends on which probability distribution you assume governs the generation of the data. And we're going to give, as I said, some examples, and we're going to start now. So there's a second comment that is really important. In practice, let's assume that you only toss the coin 3 times. and you only see heads. This can happen. Are you going to say now that the probability of head is 1 and the probability of tail is 0? Probably not. Probably you'll say, well, you didn't experiment enough. Or it could be that the probability of head is really 0.99, and it's very likely that you'll toss it even 10 times or 100 times and you'll never see tail. Do you want to say that the probability of tail is 0? Maybe not. So dealing with these two extremes, one, small samples, two, extreme probabilities, is done by something that is called smoothing. Basically, moving things away from 0. And there are multiple ways to do smoothing. We're going to talk a little bit about it, but the important thing is that you want to do smoothing. You don't want to just use the data as is, but rather to move things away from 0. Okay, so before I move on, I want to remind you of a couple of probability distributions that hopefully you've seen before. I'm going to use them in my next example, so I'm reminding you. So two of them we actually just saw now. One of them is called Bernoulli distribution. What is Bernoulli distribution? Think about tossing a single coin. Right? So a random variable, the random variable x can be either 0 or 1, or head or tail. It's 1 with probability p, it's 0 with probability 1 minus p. The second one is binomial distribution, which basically means think about tossing many coins. So the question is, how many times did I get head? Right? So this random variable takes values 1 to n. I toss the coin n times. Should have been 0 to n. Representing the number of successes in n Bernoulli trials. And we know that the probability of k successes is n choose k, p to the k 1 minus p to the n minus k. So these are two probability distributions you want to think about. And you can see the relation between Bernoulli and binomial also. The same thing, so basically, binomial is the sum of n Bernoullis. Similar relations I can see with this pair of probability distribution. We can think about categorical distribution. So now think about a random variable that can take values 1 to k, where the probability of it being I is pi. The sum of the pi's is 1. So this is really, think of a dice, right? So 6 sides, the probability of each side is something, let's say 6. The sum of them is 1. And multinomial distribution is to categorical distribution what binomial was to Bernoulli in the previous slide. So in this case, I have a random variable that can take values that indicates the number of times I got I when I did n trials. So how many times did you get 5 when you tossed 10 dice? So I'm going to get a vector, x1 up to xk. And it's the multinomial distribution with parameters n, comma p, where p is the pi's, the probability of tossing and getting 1 or 2 or 3 or 6. The sum of the pi's is 1. And we know that the probability of observing in n dice tosses the sequence of x1, x2 up to xk is n factorials over x1 factorials, x2 factorials up to xk factorials times p1 to the x1 up to pk to the xk. And again, think about taking the dice, the 6-sided dice, and tossing it n times, and then observing the n outcomes, the vector of n outcomes. Okay, so again, I'm hoping you've seen all this before. If you haven't, think a little bit more about it. I want to use it in Bayesian learning. So this is my next example. So my next example is something that you could imagine happened last week when we talked about discriminative learning, but now we're going to talk about it from the Bayesian learning perspective. So here is the game we're playing now. We're given a collection of documents. The documents are using just 3 words, A, B, and C. All the documents have exactly n words. I'm simplifying things. Either A or a B or a C. We're given a collection of labeled documents. So each document comes with a label, yi, where yi is 0 or 1, indicating good or bad. Is this a good document or a bad document? Okay, so that's the data. What am I going to do here? Eventually, after I learned from this data, you're going to give me a new document, and I'm going to predict whether it's a good document or a bad document. Okay? So far, simple binary classification problem. Okay? You can do it. Right? In fact, you've done something like this in the homework already. But now we're going to model it as a Bayesian learning problem. So what does that mean? We're going to model it as a multinomial, or the generation of the documents as a multinomial process. I'm going to call it here multinomial bag of words. And that's what I mean. So I'm going to assume that I have a multinomial distribution that governs the generation of this document. So in a given document, I'm going to have AI A's, BI's B, CI's C. So in the ith document, di, I have AI's and BI and CI, A, B, and C. The sum for all I, AI plus BI plus CI is N, is the size of the document. And how do I generate it? Basically, if you tell me that the document is good, I'm going to have probabilities for A's and B's and C's. If you tell me that the document is bad, I'm going to have probabilities for A, B's, and C's. Makes sense, right? So the distribution in good documents is going to be different than the distribution in bad documents, right? Otherwise, I won't be able to distinguish between them. And I'm telling you that if the document label is 1, the probability of observing the document di, given that its label is 1, is multinomial, which means in the ith document, I've seen AI A's, BI B's, CI's B's, CI C's. So the probability is n factorial divided by AI factorial, BI factorial, CI factorial, times alpha 1 to the power of I, beta 1 to the power BI, gamma 1 to the power CI, where the alpha, beta, and gamma are the probabilities of observing A, B, and C in a y equal 1 document. So again, now I have 2 camps. I have y equal 1 documents, y equal 0 documents. In the y equal 1 document, both of them have n characters. Both of them have only A, B's, and C's. In the type 1 document, the probability of observing A is alpha 1. The probability of observing B is beta 1. The probability of observing C is gamma 1. In the type 0 document, the probability of observing A, B, and C is alpha 0, beta 0, gamma 0. And therefore, the probability of observing DI is this. Okay? So now it's a generative model. And these are the probabilities. So what happened here? I assumed a generative process for the data. Not exactly, I don't know exactly the generative process. I know that it has this form. I don't know what is the alpha what are the alphas, the betas, and the gammas. But I know that it has this form. What's going to happen now is I'm going to see a lot of examples. And given that I believe that this is the generative process, the data will allow me to compute alpha 0 and 1, beta 0 and 1, gamma 0 and 1. Once I do this, I know everything. You give me a new document, I can figure out whether it's a 0-type document or a 1-type document. Yes?
So alpha 1, beta 1, gamma 1, and then alpha 0, beta 0, gamma 0, sum together to 1, like is 6, or?
So let's think a little bit about it. So what is alpha 1?
Is it the probability of A given that the level Y is 1?
No. Yeah, it's the probability of observing A in a type 1 document. What is beta 1?
Observing B in a level 1, and then with C.
Okay. So now that you said it this way, should alpha 1 plus beta 1 plus gamma 1 be equal to 1? No. Let's take votes here. Should alpha 1 and beta 1 and gamma 1 sum up to 1? Let's say it again. Let's say exactly again what is alpha 1. It's the probability of observing an A.
It should add up to 1, given that because it's conditioned on Y equals 1.
Because I have to see something, right? Every time it's either an A or a B or a C, no other option, right? So it has to be that they sum up to 1, okay? Because I'm generating something here. The only options I have for a word in the document is either be A or B or C.
So we also multiply somewhere by the marginal probability of Y equals 1 or Y equals 0?
Just a second. So here all I talked about is how I generate the data or how God generated these documents, right? So we agreed that it's going to be multinomial distribution. We just don't know the parameters of the multinomial distribution, but we know this is it. Had you known these 6 parameters, everything is going to be well defined. All you know, though, is the family of distribution, not the specific parameters. But once I'm going to give you enough examples, you'll be able to estimate the parameters. And that's what we're going to do now. So the first thing I want you to make sure is that you understand the game. The game is there is an assumption on a generative process or a family of possible generative process. You are going to estimate using data the specific parameters, and then you're done. You know the exact distribution, and whenever I give you a document, you can compute what's the probability that it's a 1 document, what's the probability it's a 0 document. It's exactly the same game we played with the coin, right? I told you 2 options, a fair coin or a 0.6 head coin, and then I gave you data, and you use the data to decide the parameters. Once you know it, you can make predictions on any coin toss, what's going to happen, what's the likelihood of head or tail. So so I'm saying this here explicitly. Unlike the discriminative case, the game is different. In the discriminative case, you would not involve these alpha, beta, gammas at all. You would just take your data, the 1 labeled documents and the 0 labeled documents. You'll extract features, and you'll send it to your favorite learning algorithms and train it. Here, you make a little bit more assumptions about how the data was generated, and now you estimate the parameters. So we made assumptions about how the data is being generated, multinomial with alpha I, beta I, gamma I's. Now we observe documents, estimate the parameters, and once we have the parameter, we can predict the corresponding label. So let's do it. Let's just estimate 1 parameter. So once we do this, the classification problem is computing P of Y given D. But we already know D, so it's easy to compute P of Y given D. So We're going to use Bayes' rule to do it. But, of course, we need to know the parameters. So let's compute the parameters. So we're going to compute the most likely value of the parameters by minimizing, as before, the log likelihood of the observed data. What is the probability of the data? And there's one technical thing here that is important. It's the product over all i's, P of yi, comma di. I'm assuming that the documents were generated independently of each other. So the probability of the data is the product over all data points. This is, I can write this as the probability, the product over all I, P of d given y times P of y. Now, I'm given labeled data. So I can compute this. I need to add one more notation, which is, what is P of y here? What is the probability, the prior probability of a document being 1 type or 0 type? I'm going to call this eta. So the probability of yi being 1 is eta. The probability of it being 0 is 1 minus eta. So now I can plug this in. So the probability of y comma d is what? So how do I compute the probability of y comma d? I have to split it to two options. Either y0, compute it with the alpha 0, beta 0, gamma 0, or the probability is 1, compute it with the alpha 1, beta 1, gamma 1. Right? So that's what I'm writing here. I could write it with an if statement. If y is 1, the probability of y comma d is this. If y is 0, the probability of y comma d is this. I don't want to write it with an if statement because I want to be able to compute something with it. So I'm using the following trick, and this is an important trick. So I'm writing it as, this is the case where it's 1. You see, it's eta, which is the probability of yi being 1, times this fraction. And here is the product with the alpha 1, beta 1, gamma 1. And I'm raising this to the power yi. What does that mean? If yi is 0, it means that this is 1. If yi is 1, it's just this. And I'm multiplying it by the same thing for the case of 0. What is the case of 0? This is P of y being 0, 1 minus eta. This is the constant. And this is the probabilities with alpha 0, beta 0, gamma 0. I'm raising this to the 1 minus yi. What does that mean? If yi is 0, I'm taking this. It's going to be exactly this product. If yi is 1, 1 minus this is 0, so all this disappears. It becomes 1. So you see, so I add this product of two things, which allows me at the same time to write both the case that it's 0 and the case that it's 1. You see this? So that's an important trick. It's not the only way to write it. As I said, I could have written it with an if statement. I can write it as a sum, but I want to write it as a product, and we're going to do something like this in the future again. It's an important trick because I want to take log of this. So I like to write log of products. So you have to convince yourself that you agree that this is a concise way to write these options. Either it's 1 or it's 0. I don't know which one, so I want to write it in all compactly in one expression. OK, so now I can compute the log of this. So I compute log of PD. Because it was a product, now it's the sum of, from the first part, I get the yi times the log, the sum of the log of all of these things. So it's log eta plus some constant, which comes from this fraction, the factorial fraction. I don't care about it now, plus ai log alpha 1, bi log beta 1, ci log gamma 1. And the same thing for the second part, only with the prefix 1 minus yi. And the same thing with the alpha 0, beta 0, gamma 0. So that's the log probability. Now I have to differentiate it relative to each one of the 3 parameters, and I'm going to get it. So let's do it relative to eta. It's the simplest one. Sorry, relative to the 7 parameters, because I have 2 alphas, 2 betas, 2 gammas, and an eta. So I'm doing it relative to eta. And what do I get? If you believe this thing, you see everything disappears except for these 2 parts, which gives me yi over eta minus 1 minus yi over 1 minus eta. I want this to be 0 because I want to maximize it. And if you solve it, you get that eta is the sum of the yi's divided by m. Think about it. What does that mean? Can someone try to say this in words? What is the sum of yi divided by m? So yi can be 1 or 0. I have m documents. So what is the sum of yi? The number of good documents, the number of 1 documents. Right? In this sum, the 0 do not contribute. The good contribute 1, so I get the number of good documents divided by m, and I got this to be eta. Make sense? Yeah, I mean, I defined eta to be the probability of good document. So just like with the coins that we've done 10 minutes ago, it should make sense to you that the probability of a document being good is look at your data, and out of the m documents, count how many of them are good. Take this number, divide by m, that's the estimate. Okay? Now, you could do the same thing for each one of the parameters, and you will do it in the homework. I'm not going to do it here. But it's as simple as this, and everything makes sense, just like this. I hope it makes sense. And one thing that I want you to take into account when you do it, really there are 6 other parameters, but they are not independent. They are not independent because we dealt a few minutes ago with the question of do they sum to 1, all the alpha 0, beta 0, gamma 0, and the same for the 1s. Yes, they do sum to 1, and therefore they are not independent. So you have to really think a little bit about how you do this, given that they are not independent, but again, not too difficult. Okay, so that's basically it. I have a couple more examples that we'll go over next time. Final questions? Okay, so have a good Thanksgiving. See you next week.
The lack of independence, like you're saying there's no, what is not independent? You mean
The parameters
the parameters?
are not independent, right? Because they sum to 1. So I cannot choose any alpha 0 between 0 and 1, beta 0 between 0 and 1,
okay,
gamma 0.
among them. Okay, so I thought you meant across the 2 categories, but those
No.
those
The 1s and the 0s are independent, but all the 0s have to sum to 1.
Yeah.
Right, this was your question,
Yeah.
right? So,
But what is that?
so if
Why
I
is that
already...
that must be true, right?
Oh, it must be true, yes.
Yeah, so
That's my
what-
assumption on the model, right? So if I already know alpha 0 and beta 0, I already know gamma 0.
But then, like for example, when you
No,
look
this
at
will not. No.
when you so in this multinomial example, it's like you are already making an assumption about what is the model that describes the data, right? You're
Yes,
already
yeah,
fixing
yeah.
that,
I
so you're
fix
not
the
being
model.
Bayesian about that, because otherwise you would have to be multiplying by the marginal probability that for probability of little h, right?
No.
But you're not doing that.
No. So here I have, I decided that this is the set of all models. All the models are multinomials.
Yeah, exactly.
And now I'm making a prediction on the y, right?
Yeah.
So I'm Bayesian about the y's.
So you still have, you're Bayesian about the y's. The y,
Well, I'm basing it about the y's and all the other 6 parameters, right?
but the y
That's what
here
I'm
is
basing
the
it
true
on.
label. That is
Yeah,
your,
but really I'm basing it about all the 7 parameters.
but you're not being Bayesian about like h anymore.
True.
You fixed h.
I fixed that. Yeah.
But you
So-
can you go the
and-
other
and
way
by the
around?
way- by
can
the
you
way-
say, I will fix this? No, you cannot. Can you fix the
But-
y
but
and
by
then
the-
be and then vary the h only, or can you do both?
So let's. So basically, I don't have priors. That's what you're saying.
Yeah.
You're right. I don't have priors. If you go back to the coin problem
Yeah.
that I did earlier,
Yeah.
the infinite case of the coin, I also didn't have priors, right? I told you the p can be any number between 0 and 1.
Yeah.
I did not put priors on it. Had I put priors on it, the math is going to be a lot more complicated, and I would get smoothing automatically. I didn't get smoothing also, right? I had to tell you something about smoothing, which is a hack.
Okay.
Really, I think I have a slide on it here. You can assume prior on the parameters. So think about here. What is eta? What is eta? Eta is a number between 0 and 1, but I didn't put any prior on it.
That's what your output is of this, right? That's
No,
what
but I didn't put prior on eta. I just told you,
you discovered it through the data,
right. But
through the parameters. So you
But I could have a prior on eta, I could have a prior on the alphas and the betas and the
Okay.
gammas, and I don't.
so it depends how complex you want to make the stuff.
Right. So in this case, I'm not making
But
this.
this seems like neural nets in a sense like becomes like so much more of an art than a science, right? Like I mean, what are you gonna be?
Well,
what are you gonna have
it's
priors
very
on? How are you
science.
gonna get the
Oh,
priors?
yeah, yeah.
I mean,
No question, no
all this
question.
stuff becomes like a
Right.
up.
Yeah, that's true. That's true. But it's you have to make assumptions, right? So in this case, I made the key assumptions I made is how the data is generated, right? I gave you a family of possibilities. And by the way, but I decided not to put prior. So all the members of this class of multinomial distributions are equally likely to me. Okay?
Yeah.
As I said, I could make it more complicated.
I'd say maybe it's multinomial, maybe it's something else. Maybe
No, I could, even within multinomial, right? As I said, I could put a prior distribution on the etas, on the alphas,
yeah,
and the beta, and the gammas, and I didn't. This would have made the math a lot more complicated, and really, in most cases, less realistic, right? Because I really have no clue. Now, sometimes you do have clue, and you say, you know what? I know that most of the documents are good. So I want you to work under a prior that,
But the
you know,
beta is 0.7 or whatever.
yeah, or at least greater than, I don't know, 0.75 or something.
Okay.
You can do it. I mean, the tools are there. It's just all the math is becoming harder.
Got it. And then in practice, do people use sometimes Bayesian approach, sometimes direct, or is it more like you are just like in the religion of Bayes, and then you just do that, and then other people in the religion of something else, and then they only do that?
It's quite like that, although some people
Are
change.
intellectually
And
curious
also,
and
as you will see, the approaches are not that different. So next week, I will show that with a Bayesian view, I get to something that is extremely similar to discriminative. You can really explain Bayesian perspective using discriminative tools.
Is discriminative then like frequentist, or you cannot just divide it like
No,
that?
no, it's not.
No.
It's discriminative means direct learning,
Okay.
like SVM or perceptron.
But
or
in machine learning, is there a way to, is there like a frequentist Bayesian thing, or no? Or it's just like doesn't fit those categories?
Well, everything is really frequentist, right? If you think about it, because that's
Would
what
Bayesian agree? Would Bayesian agree?
they will not agree, but what they really do in practice.
Yeah.
So conceptually, they will disagree, but in practice, if you think about what's being done, it's frequentist.
Because you're saying that they update their priors based on frequentist arguments.
Yeah,
Like
we
the
are
more
counting all the time.
coin tosses they see,
Yes.
the more their priors they change
Exactly.
their posterior, whatever. But then it's based on
Yeah. So even if
So
you
you're a
don't want to
frequentist,
be,
I know.
well,
Yeah.
even if you want to be Bayesian,
Yeah.
you're a frequentist, I think, in practice. So,
Well, what if you know every parameter for like a coin toss? Like in a coin toss, it's a phenomenon that we can technically measure and exactly know what the outcome is. It's something that is like.
oh, if
there are
you,
like
if you know the
equations-
physics.
Yeah,
if
if you know the physics, you can exactly. There's like a video that they made in one of the universities that they made a machine and
That's
there's
really
a force
perfect
and it
to the-
perfectly matches like what they can predict the outcome. 'Cause
Yes,
they know
but
what.
because there's no wind.
Yeah, I mean they have like a
it's,
perfect scenario.
yeah, probably. And, but even that, I find it hard to believe that they analyze the coin. Well, I guess you
I
can
think
analyze
it's almost,
the
yeah.
coin.
Yeah, you can
Professor
get the
mentioned that
quant,
there's a
you can
paper
get the
there,
weights,
and they
you
did
can
like
do, yeah, there's
so many millions of experiments, and it's almost perfect, right?
Yeah, that's actually, it
But
shows
then
you.
would it be then would the frequency matter? Like I mean, how do we know? I guess they also did. So science is based on frequency, right? I mean, you do tests to realize F is like you do measurements,
so
and then
that's why I'm
that's
saying
based on
Look
the
at
frequency.
standard
Yeah, yeah,
errors,
yeah.
like you're doing.
This is why I'm saying that even when you're a Bayesian, in real life,
It's also based on how many
Yes.
times this happens. You
Right.
you just assume that this always going to happen. Like if equal ma, it's
right,
always
right.
gonna
So you have some conceptual view of why things are happening this way, but really that's what you're doing, right? You're counting.
and the more it happens, you more confident you get.
Yeah, yeah.
All right, so how
Really
do
question.
Yeah, it's SVM. It's so for the hard SVM, support vectors are they these lines or
Oh, there's a point.
they're the points?
Yeah.
They're the points are the closest.
Yeah, vector. Each point is a vector,
Okay,
right?
so they're the points and not these lines.
No,
But
no, no.
these are the lines that we are like
They are imaginary lines.
lines that would
Yes.
show us the boundary of where the.
Or no, these are imaginary lines on which the support vectors lie.
Makes sense, right? So it's for soft SVM, we have a C parameter that kind of makes us like how we treat getting an example wrong, like how acceptable it is for us to get it wrong.
Tuning parameter for your optimization.
Yeah.
Right?
But I guess my question is, if C is really large, we are saying that if C is really large, we want to make sure C is really large. What matters to us a lot is to get everything right.
Yes. Because the psi I, if they are not tiny, C being large, this component of the sum of two things, is going to be so big that it's going to dominate, right? You don't
So
want it.
in the homework, it's asking if C goes to infinity. That technically means there's no margin, or there's negative margin. That's what I'm confused about. So like,
Yeah, so in fact, it's a little bit counterintuitive. When C go to infinity, only then it becomes the hard SVM, right? It's counterintuitive. You would expect that when C is 0, it becomes the hard SVM,
Yeah.
but it's not.
how? Because the equation is
Yeah,
then-
so it's really counterintuitive because when C is infinity, it means I'm not allowing any psi to be non-zero because I want this component to be 0, the product of the infinity with something. So I must have psi being 0, which is the hard SVM.
So you're saying if C is large, we don't want margin to be large. Like we're limiting the margin.
We are limiting the errors.
We're limiting the error, which will lead to limited margin, right? Like we are accepting lower margin.
No. Yeah.
We're accepting
I'm
lower
showing
margin
you
so we can
True,
get
true.
more correct. If
Right.
it's not that really separable. Like let's just say darling.
Yeah, but I don't want to think about it as changing the margin
Because the question is
because
asking
at the same time I'm also minimizing
For me, I can't do anything.
W2, W squared,
Yeah.
right?
Yeah.
So I want to think about it as I want to prevent mistakes. How do I prevent mistakes? Yes, I may need to shrink the margin.
Because the question is asking what happens to margin and support vectors when C is infinity, 1 and 0.
Okay.
Between 1 and 0, right? So intuitively, when this is 0, I thought it would be hard SVM. It would be,
So it's actually counterintuitive.
yeah, so you're saying when C is infinity, it will be
becomes
hard
hard SVM.
hard SVM. And when it's 0, it becomes,
When it's 0, basically you say, I don't care about mistakes at all. All I care is about the norm of W.
but wouldn't that be as hard SVM? Because we said hard SVM, like we said if there is an example here, like it would mess everything up. Like, because we are, let's have a data now, and then a new data comes in, and it's not in any of these ranges right here.
So the question is the data linearly separable or not? If the data is linearly separable, then 0 is just harvesting.
If it's linearly
But if it's not linearly separable, what happens when C is 0? Right?
we don't care.
It says, I don't mind. I want to minimize W, which means I'm going to open a fixed operator, and I'm going to make some mistakes. I don't care.
But that would lead to bigger margin, right?
Yeah, big margin. Yeah, I'm going to open a big margin.
Okay, so if it's big margin, wouldn't it just be hardest VM? The whole idea of softest VM
No,
was
no,
to
no,
lower
no.
the
In
margin.
hardest VM, it's big margin with no mistakes.
And softest
here,
VM,
in
it can be
softest
either,
VM,
it can be so many things. It can be,
no, but under the, okay, we can split it into two cases. But if you do, if you're not linearly separable,
if you're not
the case of